Volcanoes. They are, without a doubt, one of the most powerful and, honestly, mysterious forces on our planet. For centuries, we've just stared at them with this mix of total awe and, let's be real, a lot of fear. But these days, we need to do more than just stare. We need to understand them. So today, we're going to dive deep into the incredible science of how we actually forecast when one of these mountains is about to wake up.
And right away, you hit the biggest challenge, don't you? All the real action, the magma churning, the pressure building, it's all happening miles beneath our feet, completely hidden. So how in the world do scientists peek inside these sleeping giants to see if they're starting to stir?
Well, the answer is actually something you might find pretty familiar. They basically treat the volcano like a patient. They give it a full-on health checkup. They use a whole suite of tools to monitor its vital signs. Take its pulse, check its breathing, look for any swelling. It's medical science, but for a mountain.
Okay, so this checkup, it starts with the most basic senses we have, sight and smell. What can we actually see happening on the surface? And what can we, smell in the air? These are often the very first clues that something big is starting to change.
Visually, it's a two-part strategy. On one hand, you can't beat having trained volcanologists right there on the ground. They can spot things a camera would totally miss, a tiny new crack, a weird color in the steam. But they can't be there 24/7. It's dangerous, the weather's a mess, and that's where the remote cameras come in. These things are bolted to the mountainside, sending back images every 10 minutes, day or night. That gives scientists a non-stop visual record, which is absolutely crucial for catching those slow, sneaky changes over time.
All right, so next up in the checkup is geochemistry, which is really just a fancy way of saying we're going to analyze the volcano's breath. As magma moves around way down deep, it releases this whole cocktail of gases, and these gases float up to the surface and escape, giving us a direct chemical fingerprint of what's going on way, way below.
So here's how it works. You've got this magma deep underground, and it's releasing gases like carbon dioxide and sulfur dioxide. So scientists will fly planes right through those gas plumes, or they'll set up ground stations that are constantly just sniffing the air. The number one clue they are looking for is a sudden change in the mix of those gases. A big shift can be a huge red flag that a fresh, gassy batch of magma is rising up from the depths, basically priming the volcano for an eruption.
Okay, so beyond just seeing and smelling, scientists have to feel what the volcano is doing. And this means tracking every single tiny bulge and rumble as that mountain literally flexes under pressure from below. So as magma shoves its way up, it has to make room for itself, and that causes the ground above it to swell up like a balloon. Now, you can't see this with your own eyes, but our instruments definitely can. We've got these super precise GNSS stations. Think of them like a super-powered GPS that can detect the ground moving by just a few millimeters. And at the same time, we've got satellites whizzing overhead using radar, a tech called INSAR, to create these incredible maps showing the whole mountain inflating or deflating.
But of all the vital signs, the most direct, the most telling one, is the volcano's heartbeat, its earthquakes. See, magma doesn't move smoothly underground. It breaks rock, it forces open new cracks, and it sends all these vibrations out. And by listening really, really closely, scientists can figure out exactly what's causing all the shaking.
And get this, not all volcanic earthquakes are created equal. Seismologists listen for specific sounds. You have volcano-tectonic quakes, or VT quakes. Those are the sharp, high-frequency crack of brittle rock breaking under stress. Then you have long-period quakes, or LPs. They are much lower frequency, more of a deep hum. And that's caused by magma and gas sloshing around inside the volcano's plumbing. And then there's tremor, and that's just a constant vibration, like a truck engine that never turns off. That's a big one. It often means magma is flowing steadily, on the move.
So, here's the most important point of all of this. No single clue is a smoking gun. A swarm of earthquakes by itself, it might mean nothing. A change in the gas could be temporary. The real magic, the art of the forecast, happens when scientists take all these different pieces of data and weave them together into one coherent story.
And hey, you don't have to take my word for it. The Global Volcanism Program puts it perfectly. It's the combination of techniques that leads to successful predictions. It's when the ground is swelling and the gas is changing and the earthquakes are getting more frequent and closer to the surface, that's when scientists really start to pay attention.
And you want to see a perfect example of this in action? Look no further than the 1991 eruption of Mount Pinatubo in the Philippines. For weeks, scientists tracked a dramatic spike in earthquakes. They measured huge clouds of sulfur dioxide gas, and they saw a new lava dome growing at the summit.
By putting all of those clues together, they made the call. They made a successful forecast, and they convinced the authorities to evacuate everyone nearby just before the second largest eruption of the entire 20th century. I mean, think about that. This wasn't some academic exercise. This science saved thousands and thousands of lives.
But we have to be realistic here. This science is absolutely incredible, but it is not a crystal ball. Every single volcano is different. They all have their own personalities, their own quirks, so even with the best monitoring in the world, a truly reliable forecast is usually only possible, a few days, maybe a week at most before an eruption.
So, where does the science go from here? Well, the goal is pretty simple. Get a sharper, clearer, and faster picture of what's happening deep inside the volcano.
And that's exactly what's happening. Just look at the Pacific Northwest Seismic Network in the U.S. Back in 2014, they had about 240 stations. Today, they have almost 700. More stations means more ears on the ground. It means seismic waves get picked up faster and with way more accuracy, which helps not just with volcanoes, but with public earthquake early warning too.
And it isn't just about having more instruments, it's about the quality. One of the network engineers put it perfectly. He said, replacing one of the old seismometers with a new one is like upgrading from a fuzzy black and white TV to a crystal clear 4K TV. The level of detail they can see now is just on a whole other planet.
So the next frontier, the next great adventure, is taking this new 4K view to the most remote places on Earth. We're talking about hiking gear up to the top of isolated ice-covered volcanoes, expanding our networks down to the unexplored ocean floor, and putting instruments on volcanoes we used to think were quiet, just to find out if maybe they've been whispering this whole time and we just weren't there to listen.
And that really brings us to a final incredible thought. For the very first time in our history, we are building the tools to truly listen to the deep, slow pulse of our own planet. And as that ability gets stronger and sharper, you just have to wonder, what other secrets is the Earth going to tell us next?